Hi there! Welcome to the 43rd episode of the Synth project where we are building a synth together. In the last episode we continued to build up on the MIDI module design and prototype, but we stopped shy of running a practical test of the synth itself. It is now time to do that and to review the results, making if necessary some adjustments. Let's begin! Let's start by connecting the MIDI module to the rack power supply through this temporary adapter. Then we need to turn on the audio amplifier, which is off screen, and the synth itself. At this point we need to run some patch cables to connect the MIDI module to the synth. First of all, the USB cable from the MIDI keyboard. Then the CV output of the module to the VCO input to control the frequency of the oscillator. Let's also add to the VCO input a steady voltage to adjust the octave at which we want to play. Now we need to connect the gate signal to the control input of the VCA embedded in the VCO, so we will hear the sound only when a key is actually pressed. And now let's try to use the keyboard. Oh well, the pitch is too high, so let me adjust the steady voltage at the second input of the VCO. Okay, that's better. The notes are played in the same sequence as the keys, which is fine, but I hear something anomalous. Yeah, you see, when I hit the second key, I hear its note instead of the one with the lower pitch. The keyboard should have a priority on the lower pitches, not on the highest. And there is also a problem with the gate signal. Can you hear that? Although I'm hitting all the keys, if I go too fast we cannot hear all the notes, and that's because the gate signal is removed when certain sequences of keys are played. This is something that needs to be fixed in software, so I need to go back to the drawing board and figure out what's wrong and how to fix it. Let's start by revisiting the flowchart of the current software, and in particular the section related to the not on and not off MIDI messages. When the MIDI module receives a not on message, it increments the number of notes being played, named here active notes. Then the value of velocity is mapped to the range needed to control the synth, and then the pitch CV is emitted and the gate signal is brought high. After that, the value of the mapped velocity is emitted on the corresponding analog input. In the case of the not off message, we look for the presence of active notes. If there is at least one, we decrease the number, and we continue on the same branch as the one following when there is no active note. When there is no active note instead, we actually have nothing to do, but since we received the not off message, there must be some sort of out of sync situation. In such a case, we can easily bring everything in sync again by following the same path followed when we need to stop the current note being played. And that is practically done by emitting a 0V CV, here represented by this stop note. At this point, we need to figure out if this was actually the last note being played, or if there is another key being pressed. So we check again the value of active notes, and if it is set to 0, it means that there is nothing else to be played, and we lower the gate signal. If instead there are other notes that need to be played, we leave the gate high and we go back to idle. And here there is a problem. You see, if there is another key being pressed, although we know there is one and we keep the gate high, there is nothing in the diagram that will make that other node play. So we need to fix this problem by storing the value of the next note to be played, so we can make it play when the previous one is stopped. And we also need to compare if the note being played is of lower or higher pitch than the next note we want to play. In the case the note being played is lower pitch, we let it continue and we store the value of the new one. But in the case the note being played is of higher pitch, then we store its value as the note and we start immediately to play instead the note just received. All of this while we keep track also of the velocity of the two notes, and we keep the gate signal at the correct level every time. Unfortunately, we need to make some radical change to the software to be able to do that. The one I wrote last time was too simplistic, and as we experienced a few minutes ago, does not perform as it should. Okay, here is the new flowchart that I made to fix the flaws of the previous code. Yes, I know, it seems much more complicated than the previous one, but please bear with me, you'll soon see that it is not really that complicated. Here we go. Let's start with a note on message. Because we need to play a new note, let's immediately increment the number of active notes. Now, we need to check if this is the only note that needs to be played, or if there are already other notes received in previous messages. For that, we check the value of active notes. If it is greater than 1, it means that there is more than one note, and so we need to decide which one to play and which one to store for later. If active note is not greater than 1, it means instead that the note we just received is the only one that needs to be played. And in such a case, we store its pitch in current note, we store its velocity in the current velocity after doing the mapping, and then we execute the subroutine play current note, which will take care of generating the control voltage for the pitch and for the volume level, which is basically the mapped velocity. Back to the initial test, if active notes is greater than 1, we need to do something different. First, we need to check if the pitch of the current note is lower or higher than the pitch of the new note. This test will ensure that we respect the rule of giving priority to the notes of lower pitch. So if the current note has a pitch lower than the new note, we store away the value of such new pitch in the variable future note. And we do the same for its velocity. Then we go back to idle, leaving the MIDI module generating the control voltages for the note already being played. If instead the current note has a pitch higher than the new note, we will need to store away the pitch and the velocity of the current note, and we need to play instead the new note. So future note and future velocity will assume the values for the existing note, and instead current note and current velocity will assume the values of the new note, and we will finally call the subroutine play current note to let it play. Let's now look at the note off message. Before doing anything else, we need to figure out if there is actually a note being played or not. If there are no notes being played, it means we are out of sync, and we need to attempt a fix. For that, we call the subroutine stop notes, and then we go idle. If instead there is at least one note being played, we decrease the value of active notes to indicate that there is going to be a note that will be stopped. The point is now to figure out which note will need to be removed. The one being played, or the one possibly stored as a future note. For this we check the new value of active notes. If the value is now 0, it means that the note currently played is the one to be stopped and there are no more notes to play. And in this case we stop the note being played and we go idle. If the value is not 0, then we will have to make a decision on which note we have to remove and which one needs to be played. We therefore check if the pitch of the note to be stopped is the one of the note being played. If not, it means that the note being stopped is the future note, and so we just delete its value and its velocity, and then we go idle. Instead, if the pitch of the note to be stopped is the one of the current note being played, then we need to retrieve the future note and make it the current note. We remove the information about the future note, which is now the current one, and then we overwrite the note being played, practically stopping the note being played and playing instead the one that was the future note. Let's now take a look at what those subroutines are supposed to do, and let's start with play current note. The job of this subroutine is very easy. It just needs to play the note, thus generating the CB for that pitch, then generate the control voltage for the volume, based on the velocity, then raise the gate signal to high, if not already that, and then generate the trigger. One thing about the trigger. I made some changes in the code also to generate the trigger via software instead of generating it analogically. However, such software changes also involve a change in the hardware. So for now, although the code is already there, since I did not make the necessary hardware changes, I will still use the analogically generated trigger for now. See, I am still debating if I want to generate it with software or with some circuitry. More on that in future episodes. For now, I'm keeping the current hardware implementation. And now let's go to the other subroutine, the one named Stop Notes. This one will simply stop the current note being played by setting the pitch CV to 0, and then will set the velocity also to 0. Finally, it will clear all the variables involving the pitch CV and the velocity CV. This in particular is the one set of actions that allows us to resync the software with the messages we are receiving, in case there is an error that caused them to be out of sync. And this is all in terms of flowcharts, which, by the way, I have drawn using the so-called SDL specifications, which are very useful when describing the behavior of a state machine, which is exactly what the MIDI module is. Let's now take a look at the code changes I made to obtain this behavior. You will see flowing on the screen also the code for the trigger software, but I will not describe it for now since I'm not sure I want to use it. This is the actual code for the Arduino 2. Let's take a look at the changes I made from the previous version used in the previous video. First changes begin on line 115, where the new variables to store the current and future note information are allocated. Note also the new variables to handle the trigger via software, but as I said before, I will not talk about this part since I am not using it yet. Next changes begin on line 184, where the two subroutines play current note and stop notes are defined, reflecting exactly the SDL diagram we have seen moments ago. After this, all the remaining changes are in functions handle not off and handle not on. Let's start with handle not off. Here, basically, starting on line 253, there is a whole rewrite of the function as per the SDL diagram we have just examined. Comparing this code with the SDL diagram, you can see how it mimics exactly the diagram itself. Similarly, changes in handle not on begin on line 308, and these too reflect step by step the logic of the corresponding SDL diagram. Note in particular the two big decision points on lines 310 and 318 corresponding to the decision blocks in the diagram, the first related to the number of active notes and the second related to the value of the pitch of the new note. Let me now compile and upload this new code to the Arduino, and let's see if these fixes solve the problems we have seen on the Synth. Okay, the software has been compiled and uploaded to the Arduino, so we can now try again with some more tests. Okay, good. You see how much smoother is the scale when I play it now? However, it looks like the problem of the priority on the lower keys has not been solved yet. It looks like I must have made some mistake when writing the code. Let's go back to it one more time. And let me scroll to the point where the decision about priority is made. These are the routines that start and stop playing a designated note. In the stop notes subroutine, I should zero all the notes and the velocity variables, not just the future ones. This has nothing to do with the priority problem, but it is better to make these changes to prevent possible other problems. Okay, this should do it. Here is the code that is supposed to decide the note to be played. Oh my, here is the problem. I wrote the test of the current and next note in the opposite way as it should be. Let's fix it. And let's now save this code as version 0.5. One quick extra check. And now we can compile and upload the code to the Arduino. Time to run some more tests now. First, let's check the priority. The MIDI interface should give priority to the lower pitch notes. Let's check that. That's right. Okay, that's the way. Okay, yes, it works exactly as expected, finally. Now a short scale to see if it is played smoothly and with no gaps. Good. A little melody. Did you recognize it? So far we have tested the generation of the pitch control voltage and of the gate signal. Let's now test the velocity. To test the velocity, I will simply move this patch cable from the gate output to the velocity output. That should allow us to modulate the output volume according to the velocity used to push on a key on the keyboard. Let's see. Note how the MIDI module is able to control the VCA depending on the speed used to push on the key. Also, when we push more than one key, the module remembers also the velocity of the key and it uses it once the corresponding note can be played. Very good. Let's now test the triggers. In order to test the trigger signal, I have pre-made this configuration. Let me show you what it's all about. I'm sending the pitch control voltage from the MIDI module to the sample and hold module. The output of this module is the one that controls the pitch of the VCO from this input. The trigger generated by the MIDI module goes to the trigger input of the sample and hold, since it is necessary to collect the sample of the pitch control voltage level. This other cable sends the gate signal to the ADSR module, which will modify it to modulate the amplitude of the VCO output through its internal VCA. Since the ADSR module also needs the trigger signal, we take it from the trigger through jack socket on the sample and hold circuit. Summarizing, I have gate and trigger signals from the MIDI module and going both to the ADSR module and to the sample and hold module. The output of the ADSR module goes to the amplitude control of the VCA embedded in the VCO. This configuration will work only if the trigger signal itself works correctly, otherwise the ADSR module and the sample and hold module won't be able to work correctly either. Kind of a more interesting way to test the trigger signal. Beautiful! It looks like everything works just fine. Let me try again with the previous melody and let's see if it becomes more interesting. By the way, did you actually recognize what it is? Write it in the comments, without looking at them first, of course, so we can see how many of you recognize it. It looks like we made a lot of progress today. Everything seems to work fine, so I think it is now time to start assembling the final version of the module and install it on the Synth rack. Well, there is still the issue of the trigger signal generation. Should I keep the analog version, or should I try the hardware changes on the prototype to make the software version work? Do you guys have any preference? Let me know in your comments, and I promise I'll keep them into consideration. In the meantime, I'll see you in the next video, and as usual, happy experiments!